In this video, we shall discuss problems on three-dimensional factors, in particular lines and planes in R3. Let us start with equation of a line in R3. Suppose a line is parallel to the direction vector V and passes through the point Q. Let's say this is the direction vector V and a point Q on the line. Now, for every point on the line which coordinate x, y, z, the coordinates of these points are given by the equations in the parametric equation. Notice the component of the direction vector a, b, c are multiplied to a parameter t for any real number t. Now we further notice that if a, b, c are non-zero, then we can rewrite, let's say, the first component. If I make t as a subject, I will get x minus x0 over a. Similarly, for the third component, z, if I make t as a subject, I will get z minus z0 over c. Now, if we do the same for the y component, we will get symmetric equation for the line. Now, for a plane in R3, suppose it has normal factor n and containing a point Q. The plane equation is given as follows. Notice that this can be simplified further if we expand the algebraic form. Since a, b, c, and x0, y0, z0 are all constant, we can put them together. And we write the rest of the terms, ax plus by plus cz. Now we observe that this is just a constant, which we can call it a d. So we have ax plus by plus cz plus d equals 0. This is the standard form of a plane in R3. Notice that the coefficient of x, y, and z are the components of the normal factor n. The distance formula between a point P outside the plane and the plane ax plus by plus cz plus d equals 0 is given as follows. Note that x1, y1, and z1 are the coordinates of the point P, where the square root of a squared plus b squared plus c squared is the norm of the normal factor n. Let's take a look at the problem 4.6.5d. Find the distance between the line and the plane x plus 2y plus 6z equals to 10. Now first we notice that if this line is not perpendicular to the normal factor of the plane, then the distance will be 0. Let me describe this visually as follows. Suppose this is the plane and the line cutting through the plane in this way, which in this case, the normal factor of the plane is not perpendicular to the direction factor of the line. The distance will be 0 because the line cuts through the plane. Hence, we should first verify that the normal factor of the plane and the direction factor of the line should be perpendicular. That is, the angle between them is 90 degrees. Or in other words, we have to check whether the dot product and dot V equals 0. Now, this can be easily verified. The direction factor of the line can be found by observing the coefficient of the parameter t. So we have 1, 1, minus half. So the direction factor V is 1, 1, minus half. And the normal factor of the line can be found by observing the coefficient of x, y, and z. So in this case, n is 1, 2, 6. Now if we calculate the dot product, we have 1 plus 2 minus 3 equals 0. So it means that the direction factor of the line is perpendicular to the normal factor of the plane. Now we proceed by finding the distance. This can be done by taking any point on the line and we measure the distance to the plane by using the distance formula from point to the plane. Now we observe that the point 3, 2, negative 1 is on the line, and we can measure the distance between the line and the plane as follows. D equals to the absolute value of 1 times 3 plus 2 times 2 plus 6 times negative 1 plus negative 10 divided by the norm of the normal factor, which is given by 1 square plus 2 square plus 6 square. This gives us 9 over square root 41, or approximately 1.4056 units. We close this video with another problem in 3D vectors called projection factor. Given two non-zero factors u and v, let's say u is here and v is there. We would like to find the projection of v onto u, or sometimes we call this perpendicular projection. Here is v prime, the projection of v onto u. We would like to show that v prime equals to u dot v over the norm of u square times u. We know that v prime will be parallel to u. Now, let's say the angle between u and v is theta, so u dot v equals to norm of u times norm of v times cosine theta. Furthermore, since v prime is parallel to u, this implies that v prime hat, the unit vector of v prime, is either u hat for theta between 0 to pi over 2, or negative u hat. That is, it is in the opposite direction of u when theta between pi over 2 to pi. Similarly, we also note that the norm of v prime will be the norm of v times cosine theta for theta between 0 to pi over 2, or negative norm of v times cosine theta if theta between pi over 2 to pi. Hence, we shall see that in the case of obtuse angle, the negative sign will be cancelled, which means that we can just consider the first case. So let's consider the case where theta is between 0 to pi over 2. Now we start with the fact that v prime hat, which is v prime over the norm of v prime, equals to u hat, which is u over the norm of u. This will imply v prime equals to the norm of v prime over the norm of u times u. Now the norm of v prime is none other than the norm of v times cosine theta. If we multiply both numerator and denominator with the norm of u, then we have this. Now clearly, by the definition of the dot product, the numerator is none other than u dot v, and the denominator is the norm of u squared. Thus, we prove that v prime equals to u dot v over norm of u squared times u.